Hello, my name is Pat Goodridge. I'm one of the sales managers here at Variohm, and I'd like to just give a short presentation on non-contacting rotary hall sensors. Basically there's two principles, one's non-contacting, the other one's true non-contacting. I will just explain the difference between the two shortly, but really I just wanted to give a quick overview on the technology itself. Basically you have a magnet which has a north-south pole. This is obviously generating a magnetic field. The magnet itself, whether it's in a non-contacting sensor, would be attached to the shaft and is suspended above two 180-degree hall chips. The hall chips themselves are overlaid in an X format, basically allowing a full 360-degree electrical output. So the principle being non-contacting is the hall chips are suspended above the magnet itself, and as you rotate the magnet, the orientation of the north-south pole changes. The electronics obviously pick up the change in the magnetic field and they convert this into a positional output. This basically allows not only a full 360-degree electrical output, this allows a wide range of electrical interfaces, electrical outputs to include both analog and digital. This also allows an electrical life, basically, which is classed as theoretically unlimited, although with a packaged solution, this would have a mechanical life to the sensor itself, which is where the two-part hall technology differs slightly. This is what we would class non-contacting technology. So this is actually a magnet. The magnet's encapsulated in a housing. This would typically fit onto the end of the shaft. You would then have the electronics located next to the actual magnet assembly. There is a small standoff distance between the two. This is the true non-contacting principle. There's physically no mechanical shaft, seal, bearing assembly, which is one of the advantages of using true non-contacting, because if there is any additional loads, axial or radial, none of that's actually applied through the actual sensor assembly itself. So this now makes the transducer theoretically unlimited life, both mechanical and electrical. There is a set standoff distance that is quite generous in relation to radial and axial alignment. And if there is a deviation from the centre of the sensor doesn't stop working. There will just be a degradation in the accuracy until there is an obvious displacement between the magnet and the sensor housing itself. There are advantages and disadvantages to both. The non-contacting technology allows a straightforward mechanical coupling interface. So if you're maybe retrofitting, then you have something that you can mechanically clamp to. The two-part obviously offers advantages not only on having no mechanical shaft bearing assembly, it also means that the ceiling is predominantly higher. You would get a better IP rating because you have the sensor. You may or may not be able to see here, but basically this is a plastic housing. The electronics are inside the actual sensor itself, and then it's fully potted and sealed. So the sensor itself is totally encapsulated within the housing, which means that we can achieve both IP68 and IP69 sealing. We have a wide range of electrical interfaces, whether that's a 5 volt or a 24 volt supply. These are completely self-conditioned, so you can take either an analog 0 to 10, 0 to 5, 4 to 20. This can in effect also have incremental pulse, PWM, SSI and SPI interfaces. So in effect they can be a straightforward analog sensor, potentially similar to a pot, but they can also be an incremental encoder and also a single turn absolute encoder. We have a wide range of housing configurations, starting from 13mm up to 91mm, really dependent on application and environment. These are predominantly made to order because of the technology, whereas you can not only have single free wire devices, these are available as redundant, so we can have specific programmable angles available between 30 and 360 degrees. These also can have specific electrical outputs to include switching functions, and these can be redundant sensors, so these can have 2 independent supply, 2 independent ground and 2 independent outputs. These are multiple use applications from mobile vehicle applications, aerospace, automotive test, through to general machine tool. As I was explaining, this is a non-contacting sensor, but you still have a shaft assembly. Obviously on the end of the shaft inside the housing itself is the magnet and the electronics. These have a bearing seal assembly, but it is an encapsulated sensor. The two-part technology, like I say, differs slightly in that you have a magnet. The magnet doesn't necessarily need to be in the holder itself. The magnet can obviously be inserted on the end of your shaft, or you can use the magnet assembly. And then you have the electronics, and you have the standoff distance. What you do tend to find is the larger the magnet, the greater that standoff distance will allow. And you will see that depending on the Hall sensor size, the larger the sensor, the larger the standoff distance can be.